In this presentation, we are going to cover red-black trees. So the prerequisite of this tutorial is that you should have information, or you should know about binary search trees, so BST. So we have covered the topic binary search tree in the previous tutorials. You can watch them in our data structure playlist. So we have studied that binary search tree will give a big O of log base to n time complexity in case of insertion or searching or deletion operation only if it is balanced. So we have understood this very important concept that only the balanced binary search tree will give us a time complexity of big O of log n. So we know that a balanced binary search tree is a binary tree which in which the difference of the height of the left subtree, I'm going to write it in short as LS, and the height of the right subtree should be less than equal to 1. So this is the basic concept behind the balancing of the trees. So we have covered how to insert and perform the search operation in binary search trees in C++, but we have not in that tutorial we have not covered how we can make a binary search tree balance. So this is a very important question, how to make a BST balanced. Make BST balanced. So now we are going to study red-black trees, which are essentially the binary search trees. So they are binary search trees, and more specifically they are the self-balancing binary search trees. Self-balancing BST. So this means that whenever you will perform an insertion operation or a deletion operation in this data structure, it will automatically balance itself, and we know that the meaning of balance is here. So it will automatically maintain this balanced state even if you insert some elements or if you remove some elements from this data structure. So how does that magic of self-balancing works? So basically, insertion operation or a red-black tree follows some rules. So basically every node in a red-black tree follows some rules. So I'm going to write here self-balancing binary search tree. So a red-black tree is a self-balancing BST where every node follows these rules. So let me just write all of these rules. So let me write the first rule. So the first rule says that the root of the tree is always black. So whenever you are going to construct a red-black tree, you will observe that the root of that particular red-black tree is always black. So you can see that red-black tree, in the name itself there are two colors, red and black. So it means that we're going to use colors to make this BST balancing. So to make this data structure as balancing, we are going to use red and black colors, and we are defining three major rules, and when these rules are followed you will get a balanced tree. So the next rule says that there are no two adjacent red nodes. So I'm going to use a red color to represent red nodes. So arbitrary or a red-black tree, in the red-black tree, root of tree is always black, and there are no two adjacent red nodes. So the second statement basically means that if I want to construct a binary tree or an arbitrary like this, so this is not possible because you can see that these are two adjacent nodes. Adjacent nodes means the parent node and the child node are adjacent to each other, so both of them cannot be of red color. So this is the second rule that we have defined. Let's move on to the third and a most remarkable point. It's a most important point. So this point says that every path from a specific node, every path from a node. So if I will pick up any node of this red black tree, any node of this red black tree, including the root node, even if I will pick up the root node of this binary tree or the red black tree, and I draw a path from that particular node to any of its descendant null nodes, or I should say descendant leaf nodes. So leaf nodes and null nodes are basically the same thing. So this means that if you will create a path from a particular node to the root node, to the null nodes or the leaf nodes, it will have the same number of black nodes, same number of black nodes. So I'm going to write here black nodes. So these are the three important golden points, and we're going to make use of these three rules, and then we're going to perform insertion in a way that these three rules are not violated. We will study how to insert in a binary tree. We will study the insertions in arbitrary in the next tutorial. In this tutorial, we are just grabbing our concept of arbitrary, and we are just going to look at how an arbitrary structure looks like, and then we will see how we can perform insertions in red black trees. So let me just give you two examples or two arrangements of binary trees, and then you will have to tell me in the comments below, out of these two, which one of them is a red black tree. And you're going to use these three rules. You will have to apply these three rules. So if any of these two arrangements will follow all of these rules, that means it is a red black tree. So let me just draw an example here. So we know that the root node is always black, so I'm not going to consider that situation. So now I will create some random arrangements. I'm not going to assign values. We are just concerned about the structure, because we know that the values are basically in a binary search tree form. So I'm going to draw two arrangements like this. So this one is the first arrangement, as you can see here, and in this one I will create a black node here, and now I will create two black nodes here, and then I will create two red nodes here. So these are two binary trees that I have drawn, and basically we are just representing these colors as red and black. We do not actually color these nodes. We use variables red and black to specify for each and every node that the color of this node is whether red or black. So these are the two arrangements. Now what you will have to do is just pause the video. This is an exercise for you. You will have to decide out of these two which one is a red black tree, So now if you have decided, let's now understand take a look at this first one. So the first condition is root of tree is always black. It is satisfied. No two adjacent red nodes. So you can see that there are no two adjacent red nodes. If there is a black node, then there is a red node, and then again a black. There are no two consecutive or adjacent red nodes. In both of these examples, you can see both first two conditions are satisfied. So obviously among these two, the third we are going to study the third one. So every path from a node, so we will pick up let's pick up this node, root node, and every path from this node to the one to any of its descendant leaf nodes. So you can see that this one is a null node, this one is also a null node, and this one is also a null of or a leaf node. So now we can see that there are some paths. So let's see the path. So if we are at this root node, one path is from this node to this one and to this one, and the second path will from this node to this one and then this leaf node, and the third path is this one. Now we will have to see that in all of these three paths, the number of the black nodes should be same. I'm highlighting it, it should be same. So let's consider the first path. You can see in the first path there are two black nodes, one is this and the another one is this. In the second path we go from here to here and then here, again we are encountering two black nodes. So both of these paths have two black nodes. Now consider the third one. This one does not have two black nodes, this path has only one black node. So the rule number third is violated here. So I'm writing here the number of black nodes. So rule number three is violated in this case. So number one is not a red black tree, not arbitrary. Now let's consider this second one. In the second one you can see that if I consider the root node, it is black and there are no consecutive red nodes or no adjacent red nodes. If we consider the third one, every path from a node, so let me pick up the root node including root to any of its descendant leaf nodes. I know that these four are the leaf nodes or the null nodes because they do not have any children. So I can see that this one is the first path, and in this path there are two black nodes. The second path is this one and it also has two black nodes. The third one is this one and it also has two black nodes, and the last one is this one, and even this one has two black nodes. So all the paths from the root node, from root, has two black nodes. But remember that this third condition should satisfy in all if you pick any of the particular any node. So even if you pick up this node, so I'm going to revert back this. So I will remove all the paths. Now we are not going to consider the root node. Now let's consider this node. So when you consider this node, the path from this node contains one node, and path from this node to this node contains one black node. So if you will consider this node, you can see that if you go from this node to this one, there is one black node which is including the root node. If you consider this whole subtree, the node which we have picked is acting as a root node, so it is a black node, and even in this one we have one black node. So if you pick up any node, so every path from a node including the root node to any of its descendant leaf nodes has same number of black nodes. So rule number 3 is satisfied in this condition, and even rule number 1 and 2 are satisfied. So number 2, which is this one, is essentially an RB tree. So in this manner we are going to use these 3 rules as an information to make insertions in RB tree, and we are going to follow some steps to insert in the RB tree. It's a very important concept and also an interesting one. So basically when we say that a tree is balanced, so the time complexity of a red black tree is, in the worst case also, it is big O of log base 2n, because it is a self-balancing binary tree. We do not have to worry about balancing. So that's for it for this tutorial. If you have liked the video, make sure to hit the like button and make sure to subscribe our channel, because we are going to make some more interesting tutorials and courses like this one in the future. And if you want to see our content, you can visit our website www.thinkxacademy.com, and you can even download our Android app. I have given all the links in the description below. So thanks for watching. See you in the next tutorial.